Okay, good afternoon. I'm Solomon Yim. I just want to show some of the capability that we have in terms of both experimental and numerical project that we have done in at Oregon State. And I'll introduce myself a little bit. My training is in structural engineering. I got a PhD. My BS in civil engineering, MS in structural engineering, PhD in structural engineering. And I also have a master's degree in mathematics, which is in the fluid dynamics. That's why my entire career has been doing fluid structure interaction problems. So I'll show you some examples that I have done that are related to this. And as a self-introduction, one of the projects that I did was actually analyzing damaged platform, because I know some of you are very interested. You have your own bulldog and how wave can impact the bulldog. And one of the studies that I did was actually how hurricane can impact a offshore platform. That was a before picture, very nice looking. Before the hurricane Ivan, some of you might know, 2004. And that's after. You can see a lot of damages. So bulldog, the same thing. You see that? And so we were tasked to look at actually what caused damage to the decks itself, and there's some references. So looking at here, a huge wave, what we call roll wave, due to hurricane hit, and you can see the girders damage, bent in. The front one, the second one, and the third one, you can see the damage, severely damaged. And so we went back, look at the drawings, and look at the wave, and then we actually see how it was originally designed, why it could not withstand such a wave. And we look at the dynamic pressure. They are very high due to the experiment, due to the hurricane wave. And we were actually asked to figure out what wave would cause that particular damage. So we did some experiments, okay? Generate a lot of wave and see which type of wave actually caused that kind of problems. So this would apply to kind of bulldog type problem.
Big ones.
But that is just what I did in one case. And now I'm going back to what's actually applicable to ours. Last time we actually presented this, looking at the parameters of the Willamette River margin. The natural parameters, as Pedro mentioned, that the width of the river, the depth of the water. Oh, okay. So, yeah, okay. Current speed and the curvature of the river, all those are the bathymetry, the bed material, sediment, that debris, as well as vegetation. All those we need to include in our modeling and simulation. Okay, floating bulldogs, of course, that are part of the environment. Seasonal variation, dry weather, and then you have the river. So the time scale that Pedro was talking about, measurement 5 years. And then the other ones that are important, of course, the boat, the type of boat, the speed of the boat, the displacement, the length of the boat, propulsion system, all that are important. The power production, the hot form, the navigation path, whether it's maneuvering this way or that way, and the number of boats. Some of you mentioned the 5 boats. Well, if you have 5 boats in the area, actually those cross waves add up, and they don't add up linearly. They could create very strong wave, what we call roll wave, and cause your bulldog, one big wave can cause your bulldog to go up and down and damage your dolphins as well. Okay, so again, that also is looking at the time scale. So I added a couple of columns on this. The distance between the sail line of the boat and the shoreline, that is actually also very important because there's dissipation as you move along. So if your boat is very close to the shoreline, the impact will be a lot larger. Your boat is very close to the boat dock, that will cause a lot of problems as well. So that is one important thing, the maneuvering. And the rate of decay of this kind of wave. So different boats generate different waves, and they decay differently. So even though it may look atrocious, if they're far enough, they won't cause as much problem. Okay, so that depends on the type of the boat, the speed of the boat as well. So this is what we did in past without all those high-speed boats. So this is the analysis based on far field and wake, but this is more like slower boat, what we call displacement boat hydrodynamics. But what we are facing is actually much more important ones. In shallow water, the wakes are a lot larger, much more significant compared to in deep water, where the length is the scale that causes problem. But in this case, ours is actually the shallowness of the bottom. So at slow speed, the wave looks like that, and that's very typical Kelvin wave. You will have the diverging wave that goes sideways, and then you also have what we call longitudinal wave that are following this the boat itself. But as the boat speed up, then you see this longitudinal wave will disappear because they are just shed behind. They can't follow the speed of the boat. And what you end up is with this. And this is very important because it actually causes problems that are attacking the perpendicular to the direction of the shoreline that cause a lot of wave problems. So here's looking at the speed of the boat. Okay, so at slow speed, the wave signature is rather small. As you increase the speed, you have larger and larger signature. And as you further increase the speed, then the wave will look more like that. All right, so this is increasing speed from here to here, this one, and then this. So why are they so important? Well, if you look at the angle of attack of the wave on your shoreline and your boat dock, at slower speed, it is actually more contributing, so your shoreline or your boat dock over here, it contributes more to the current, either against the current that's floating or add to the current speed. Okay? But as the speed goes higher and higher, the wave becomes larger and larger, and as you see that particular arrow perpendicular to the wave is actually hitting your shoreline almost head on. Okay? That causes a lot more of your erosion of the shoreline. Okay? So the waves are much bigger as well, and that's why I draw the arrow much longer. And then the effect is actually proportional to the square of the wave, and therefore the effect is much, much larger. So when you double, you square the double is 4 times. Okay? When you triple it, it's 9 times. That's the effect. So the higher the speed, the larger the problem. And the angle of attack is also much sharper. Okay? So we have done some of our experiments in the past. Desiree mentioned about the study by McFarlane. Actually, McFarlane did a study for Australia in 2012 for his PhD thesis. So there's already a good foundation of what has been done recently, relatively recently. He studied a speedboat, conducted a literature survey of the physics of the speedboat, and examined and developing a wake prediction, wave prediction, I should say, tool that model the physics. And then he actually developed a prediction tool that was able to cover different vessels and able to include the effect of the hot fog. Also validate against a number of experimental data. But keep in mind that this is technology about 10 years old. The boats are different, the rivers are different, and this is also more of a primitive tool, and we have more experiments now. And so he developed actually a criteria on how the effect of the boat operation on the sensitive shorelines. And he also combined some of the applications of the two and regulatory criteria for and remedial measures. So he actually makes some suggestions on limiting the boat speed and things like that, and also how to repair boat docks, and also put in riprap here and there to protect the shore. So there is a study already, a PhD study. Okay, but we need to examine how good it is for the purpose that we look at for the Willamette River mine. We have done at Oregon State University, actually, that is my experiments with my own student about 6 years ago, looking at boats. So we did that and turning. But you can see we have wakes here, we have wave, we have wakes, and maneuvering, turning in our wave basin. So I just want to demonstrate our own capability here. And we have measurement that measure the speed, looking at wave pattern and things like that. So we have done that in our wave basin. I just want to point this out. That's one of the experiments that we did. One of my PhD students 6 years back. Okay. So, and then I also have other students who did actually a simulation of fluid structure and sediment interaction. So this is our sandy soil at the bottom. We're going to have wave, and you can imagine this is a log that is dislodged, a tree trunk dropped into the river. And we actually, this is a model of an experiment. That experiment was done in Japan, okay? But the student was here, and we did some simulation. Okay, so you have wave, and you have the log, and you can see the wave log drop down there, and you can see also this interact with the soil. Okay, so we have that kind of capability. But I'm not an expert on sediment, and Professor Wilson, he will probably be very helpful in this aspect. But we have done experiments, and we have. So another example that I'm involved in, actually this was an experiment that was a high-speed ship experiment. They were designing for different hull forms, very light boat, aluminum boats, and they were concerned about the damage to the hull of the aluminum boat. So a very high-speed planing boat. Okay. So the experiment was done at the U.S. Naval Academy, and they were kind enough to give me the data. And so I built a model and a final model for both the ship, the hull, and the water. And I'll show you what we can do. And here's the motion. Okay, so generating wake, bouncing off. This is an experiment, right? So it's in a channel, and you saw the channel that we have, 100-meter long, in our wave basin. This is a very similar one at U.S. Naval Academy. So we can model the wave, the wake generated, and its effect on the boat. And I'll show you another picture. We can, in this picture, we'll be really able to show you the wave created. Okay, high speed, and now we can see the wave, right? Okay, so but this experiment was actually looking at the impact of the boat itself, but we can apply similar principles to boat docks. I think this is one important thing. Is I can add a boat dock here, and you will see we can simulate the effect on the boat dock. Okay, so here is looking at two particular speeds and how impact load on the boat would be like. This is a 9 meter per second force speed in waves. So it's going to hit waves. You can see that, right? Waves are coming. You will see it doesn't seem to be very big wave. So now you can see bouncing up and down, bouncing up and down. They were very concerned about buckling of the aluminum frame. Okay. So then we also have another speed. This is a lower speed, 7.6 seconds. So you can see the wave propagation. So we can do that, and we can simulate wave hitting a bank. We can simulate wave hitting a dock. Should not be a problem. We'll simulate the boat. The question is how well it performs. Well, this is a very preliminary case where we were only given the weight and the shape of the boat. But there was no other weight, inertia, moment distribution. And we hit it pretty well, but you can see that our Nimoto solution is not matching perfectly. But just to show you that, remember the list of parameters that I have, I've only given 2 parameters out of 10 of them. And so if you were improving on those parameters, we will be able to match it quite well. And indeed, we did. So what I want to show you is actually the importance of parameters. Okay? You can hit 80% maybe, but the big picture doesn't look as good. And we need to narrow on the parameters, improve on them, and we'll get good results. Okay, so just to say a few things. Well, starting from what McFarland did in 2012, well, how can we kind of turn it to our advantage and see how we can improve it? Well, there are a lot of things that we can do for our realignment margin. Okay, as Katie sent out the information just yesterday, well, all this information here, I need to look at to see if actually the McFarland data set include this or not, right? And how much did it include? Okay, so if the McFarland data set actually include this quite well, then we will be confident actually use that as starting point, and we'll be pretty confident that it will give us decent results. But if not, then well, we will have to look at a lot of things. How well, what did they do actually? The Tasmanian wake prediction model. What data did they use? Okay, so we need to dig into the detail and see how well it fit in ours. What they're able to do, would they be able to do the same for the Willamette River margin? And we should also look at other cases where our operational criteria and the our shoreline, our soil condition, are they similar? We have to look at all that, and then we will see how well we can apply using that as a guideline to design or control boat speed or design better boat docks, but the boat docks are already there, so we might have to see how we do upgrades. But I'm not a policy maker. I can tell you the science and tell you the effects, but the policy will be up to you guys. So, and again, other things that we want to do is see, okay, you have some measurement plans, experimental plans that we can use our expertise here to fill in the gap between that McFarland study in 2012 and what we want to do here. Okay? So looking at inclusion of some of the vessel hull forms that was just provided to us last night. Looking at other scaling issues, and see if we can actually do the same thing for the McFarland study and further improve on that study as well. Okay, and again, the one thing is important to look at the roll wave. As mentioned, if I don't think in the Mafan study they include that. There's mostly just a single bolt going on the roof. But if you are looking at multi-bolts, you have 2 bolts, 3 bolts, 5 bolts, those will have to be additional study that we should do. Because roll wave is very important when you have nonlinear superposition of 5 different bolt weight. It's not, the sum is not 5. The nonlinear interaction will cause it to be 10, 15. Okay, those are things that really need to study, and I just want to emphasize that. That's all I have. Very brief. I just want to keep us on time. I can open up for discussion. I just gave us a very comprehensive presentation on nonlinear bolt effects on structures. 2 days ago, when I was in China, that talk was 2 hours long. So I can give you a 2-hour talk, but this is long enough, right? I'll be happy to answer questions.
So I'm assuming to figure out the boat dock impact, you need boat dock data, right? Size,
Yeah.
weights, whatever
Yeah.
parameters you need.
Well, there are existing design guidelines for boat docks already, right? So the parameter we can go by with the design guidelines. That would be a starting point. But those design guidelines are, developed quite a long time ago, and therefore mostly displacement boats, Houston ship channel when you have a couple of ships moving along at low speed. We are not talking about couples boats at low speed. We're talking about very high speed. So that would be different. And we'll start with the design guideline for ship channels. That would be what I would suggest.
Okay. No, what I was talking about, the modeling, the effect on the dock, you need to have a model of the dock.
Yeah, we can model the dock. That's not a problem. But there are design guidelines for the docks, and we can look at those design guidelines, and they come from modeling as well. Yeah.
And those design guidelines must have a set of assumptions of how much force and how much action they have to.
Yeah. Well, the design guidelines, those they also limit the speed of the boat on the ship channel. So, but somehow we have not done that in the Willamette River. That's my understanding.
Well, what's interesting in this case is it's less about the speed and it's more about the weight and the depth of the hole, the displacement in the water at slow speeds, which is counter to that earlier model that you were showing, if I was understanding that right.
Yes.
So it's less a question of speed, but you've got incredible displacement with resulting big wakes.
Yes.
Not all that different in some ways than this modeling done
Yeah.
with ships.
Yeah. That's very different because we're talking about a wakeboard that intentionally create as big a wave as you can. Whereas in a ship channel, you intentionally slow down the boat to minimize the wave as much as you can. So that's why I think numerical simulation and experimental tests are very important because of the high speed. We also need measurement and observation. And so field measurements, more experimental tests, and numerical simulation, that combination will help us to understand the physics, the science a lot more.
What is true is that the theory that has been developed on boat wakes over the last 50 or more years is based on the assumption that we want to minimize the wake because the wake is an energy that we are losing and is not efficient from the perspective of the sailing ship. But now we are doing the opposite because we are not want to be very efficient, but basically what we want is to create a wake. And that type of approach hasn't been studied that way. Basically, it's very empirical. They found a way to generate a super big wave, and that is by reducing the speed and increasing the displacement fundamentally. That is not what the theory that is the status quo of the science is telling you, and that is why it's so important to have a backwards understanding of what's going on. Again, that is one of the points that is missing in the whole story, which also creates some issues with policy, because most of the policy talks about maximum speed, and they might be fulfilling the maximum speed, but not the size of the weights, and that is also creating a different conversation.
I didn't introduce myself when we went around. I'm Dr. Hinsdale, I am the civil engineering program at the University of Portland. My area of expertise is water resources. I'm really focused on minimizing the impacts of human activity on river ecosystems. So I would also like to introduce, let me just go down the side. So there's a few of us on the research team. This talk is about the study that we started working on this spring. And so also Dr. Dillon is working with me in mechanical engineering, and I have two research students, Davey Robeck, who's in civil engineering, and Rachel Anderson, who's in the back there in mechanical engineering. And we've also been working with Desiree Toulis and Derek Godwin on the methods and what we're going to measure out in the field and things like that. And of course, most importantly, the Oregon River Safety Preservation Alliance. We've had a lot of volunteers who are willing to participate in our study, which is excellent. And so with all of that research team, we've developed some study methods, and we've started doing some monitoring this summer, but it will likely continue through next year. You've kind of all heard about wave energy and erosion and all of that with all of the three previous speakers. And so the main objectives for our study was to evaluate wave energy in the different zones that were created for the Newberg Pool. So the wake surfing zones, the areas where recreation is allowed but no wake surfing, and then the no wake zones. So we have different sites. We have up to, I think right now it's about 24 sites that we're monitoring. We actually have 4 sites that we're intensively monitoring, which means we're measuring every week and going out there quite a bit. And one of the ways we decided to evaluate wave energy, as we've heard, it's a really complicated issue and something that's difficult to measure, is we installed game cameras on docks, and they're focused on a dock piling, and so we can measure the height and width of that dock piling, and that's our frame of reference. And so the game camera is triggered anytime there's motion that goes past it. So and so anytime a boat comes by, our game camera starts a video, and we're able to record the wave in reference to our stationary dock piling. And so with that, we can correlate erosion with energy based on published relationships. And you've heard all of the factors that go into play with that wave energy and how much erosion that causes. And so we're also measuring, we took soil samples for soil characterization, looking at the vegetation on the bank, the different structure, noting the different structures and all of that. And so we're able to use that to come up with an estimate or a potential erosion as a result of that wave. And so then ultimately we'd like to compare that potential erosion in different zones. So that's kind of our phase one, is the videos. We would really like to put in erosion pins to directly measure erosion, so then we can evaluate how effective our relationship is. And we'd like to put in staff gauges. Right now we're just using dock pilings, and do a much more complete study. This is more of a preliminary type of study. Okay, so this is just a map of, I just identified the wake surfing zones for simplicity. But the red dots represent all of our volunteers who are willing to help us collect those videos. The green dots are what I call the intensively monitored sites. So you can see we have one near milepost 47 in the wake surfing zone, and then one near milepost 42 that's also in the wake surfing zone. And then we have a site this site here is in the zone where wake surfing is not allowed, but other recreation is allowed. And then this one's right next to the I-5 bridge, so it's in the no wake zone. So we're able to collect data in the different zones and see overall what the cumulative impacts are. And so right now we've got, like I said, there's 24 sites, and we're hoping that we can get videos from all of those sites. Okay. So I will let my colleague, Dr. Dillon, talk about the video processing.
Yeah, and I'll just introduce myself again. I'm Heather Dillon. My background, I'm actually a mechanical engineer, but I specialize in numerical methods, mostly for video processing and fluids applications. And so what I love, I've been working with Dr. Ford for several years, and what I think is great about the genius of working on her team is that she's really good at taking a complex problem like this and, just diving right in, roll up her sleeves, let's go get some data, let's actually do the things, let's not just talk science, let's go do science. And so she actually spent the entire summer kayaking around as a volunteer in this project, and so she's been really important in this. So you can see this is a video. It looks like end of May was the timestamp we're using. This happens to be a Bushnell camera that is a game camera that was on a dock. The cameras that we're using are relatively low cost. Most of them are not the Bushnell model. We looked at a couple of different camera models, made some choices. What you're going to see in the video is you're going to see this boat come past, and we're showing you the original video up here, the sort of the raw video footage, and then down here on these two screens, you'll be able to see how we're monitoring the dock piling. We weren't actually able to put anything in the river yet because we were waiting for some permitting to come through, but as soon as it happened, it happened. So you can imagine the types of things we'll be able to do with our game cameras once we actually have a yardstick or ruler out in the middle there. So I'll hit play on this and we can kind of watch what happens. So what we did was we used different colors of tape. So here you can see